about what kind of information you can get from spectra and how could you interpret it. And then we will finally move to results. Today I hope to see the thick disk of our galaxy, tomorrow the halo, and the last day the bulge, my favorite topic for the end. So yesterday, as you might remember, we saw that from high-resolution spectra, like this one that is in the background for the sun, you could measure the abundance of some element, in principle any element for which you have line in your spectra. If you have lines of the same element, different lines, that of course correspond to different transitions in the electron levels, then you could also measure the effective temperature. Is better. Thank you. And if you have lines of the same element at different ionizations, for instance, neutral iron and iron ionized ones, then you could also constrain gravity. If you remember, this was necessary because gravity or electron pressure entered in the Saha formula that governed the degree of ionization of an element. Okay? So, I would like to spend a few more words about how, in practice, when you want to derive the Iron distribution, the metallicity distribution of a complex stellar population like the halo, the thick disk of the bulge, I mean, a population that has a spread in metallicity, not a single metallicity, then you need to sample the spread in metallicity pretty well. So, in this case, for instance, I'm showing a color magnitude diagram of the galactic bulge. It's complicated because there are many structures, but in this moment it's not necessary that you understand every aspect. Just follow me. This is the main sequence, the turn off, the red giant branch, red clump stars, so stars burning helium in the center, and this is the upper red giant branch. This stuff is foreground disk, so these are stars that are in front of us. They do not belong to the bulge. All metallicity pass by. If you take a region where only metal-rich stars pass by, then you get, of course, a very biased metallicity distribution. So, for instance, it is very common that people select stars in the upper red giant branch because they are brighter. No? We could go down there, but the further down we go, the harder it is to get a good signal-to-noise spectrum. So we want to stay up above in the red giant branch, but if we go too high, then we need to sample a huge range in color. If we stay low, so at fainter magnitudes, harder to get the spectrum, we can reduce the color range, but still we have to make sure that we sample both this region, the blue region, where metal-poor stars evolve in the red giant branch, and this, the red region, where metal-rich stars evolve. Because this will be the star, if this is, suppose that this is the metallicity distribution of the bulge, these stars will contribute to this side, and these stars will contribute to this other side. So not only we have to take stars in this whole box, but we should also make sure to sample this box evenly. Because if we do select star in this box, but many stars on this side, and just a few on this other side, of course, our metallicity distribution will be very much populated on this side, and we'll have a steep drop on this other side, not because this is the real shape, but just because we have biased our sample. So it is important that we sample this thing evenly. And now we have another little problem, because you remember that this axis that I just covered, this axis that is color, is a proxy for temperature, right? In the color magnitude diagram, the temperature increases this way. So these are cold stars, and these are hot stars. The hot stars have a well-behaved spectra. This is a high-resolution spectra of a typical star. Actually, it's not a typical. It is an actual star that I had on my computer. A star that has temperature of 5,000 Kelvin and solar metallicity. Most of bulge stars have solar metallicity, so this is fairly typical. But on the other side, this is a star that also has solar metallicity, but a temperature of 4,200 Kelvin, because it is on the red side, so it is a colder star. So you can see, and we discussed it a little bit yesterday, cold stars have molecules in their atmosphere. So the spectrum of a star in here is like that, as a continuum that is full of bumps, because there are molecules, specifically for this kind of star, there are a lot of TiO molecule, combination of titanium and oxygen, and so it is pretty hard to have a good measure of the lines in these stars, because it is very hard to fit the continuum. It is really not flat as it could be for that one. Okay, this is what I was saying. For cold stars, M giants or M dwarfs will be the same. For stars with cold temperature, if you remember in the spectral classification, the spectrum is full of molecular bands. So in the optical, it is very hard to measure abundances accurately for those stars. And this is a problem, because these are the stars that one would like to measure. These are the brighter stars of an old stellar population. On this other side, at the same magnitude, you only have very young stars. So you have no stars in the bulge, in the halo, in the thick disk. There will be no stars there, because those are only very young stars. So if you want to measure an old population with ages above 1 gigayear, not especially old, the brightest star of your population will be located on this side. But they are too cold to be measured accurately in the optical. Fortunately, in the near infrared, the situation is different, because the spectrum of an M giant in the H band, I'm sure you cannot read this, but believe me, it's the H band. These are spectra for the apogee survey, for those of you who might have heard about it. You see that even the spectrum of an M giant is relatively flat. It is still very crowded with lines, also because we are looking at metal-rich stars, so they are crowded with lines. But even at a resolution of 20,000, there are many lines, but the continuum is rather flat. So if you want to measure M giants, you should go to the near infrared. Now, high-resolution near-infrared spectrographs have been are now available since the last 5 years or so. So it is possible, well, they were available even before, but now we have multi-object spectrography in the near-infrared that allow us to measure the spectra of many stars. So we could sample the distribution of complex stellar population in a reasonable amount of time. Spectrum of K giants that also has some molecular features in the optical is still very flat and very easy to measure, in principle, in the near infrared. So that's why in what follows I will talk a lot about spectra obtained with within the apogee survey, because it has represented a significant step forward in the study of old stellar populations. Okay, this is just a slide with, you don't need to read all that, but we all agree, I think, since what we saw yesterday, that from the spectrum you can get the temperature, because the spectrum, even if you look at it, is very sensitive to temperature, and it is also very sensitive to gravity for two reasons. One is what we discussed yesterday, because gravity affects the relative fraction of an element with different degree of ionization, but also gravity affects the collisional broadening of the lines, because when gravity is higher, the density is higher, so there are more collisions. Some lines are collisionally broadened, so they are more broadened in stars with higher gravity. Why do I mention this? Because you can get gravity from the spectrum. You can get it with the elements at different ionization. You can also get it, for instance, by simultaneously fitting the wings of Balmer lines. Why do I emphasize this again now? Because if you can measure gravity from the spectrum, then you can measure ages of individual stars. And this is very important, because for what we saw yesterday, I told you that you could measure ages of a stellar population by sampling the turnoff, and then the absolute magnitude of the turnoff as a relation with ages. But to do that, you need many stars. You need to construct a color magnitude diagram and sample the turnoff. With the method of the turnoff, you couldn't get ages, in principle, of individual stars. Because an individual star doesn't draw a turnoff, right? Doesn't define a turnoff. And then you would have to, instead from the spectrum, you could measure, if you could measure gravity and temperature, you could put your star, for instance, this one, in a diagram that has log TF here and log gravity here. This diagram is very, very similar to a theoretical HR diagram because temperature is temperature and log gravity is a linear relation with luminosity. So it is almost the same if you put here log gravity or luminosity. In fact, if you draw isochrones in here, these are different examples of isochrones of different range of ages and metallicity. As you can see, they resemble a lot the turnoff that we are used to see in an HR diagram. So if you put your star there and many models here, you are able to constrain the age of the star. For instance, these stars will be this age. I don't remember which are the ages of these isochrones in concrete, but doesn't matter, no? So there is only one isochron that best fits the position of the star. So you could assign an age to these stars individually. For instance, here, I labeled it, so this is 1 gigayear, this is 20 gigayear. These stars specifically will have, this will be 15, 10, like 12 gigayear. You can constrain the age of the star. Of course, you need that the star is anyway close to the turnoff, more or less, in the subgiant branch, or just below the turnoff, because if your star is up there, you can see that the model collapses altogether, so even if you put your star there, you will not have a constraint on the edge. But so, what is important about this is that if you have a high-resolution spectra for a star that is more or less close to the turnoff, and you could measure temperature and log gravity from the spectrum, you could get the age of one individual star, even if you don't know the distance of the star. Because normally you need the distance in order to put here the stars in absolute magnitude. This time, you could get directly the gravity and put it there without knowing its distance. Since 2 years ago, there is a new method that has been proposed to measure ages from the spectra of individual stars. This method is in principle very powerful, but at the moment has huge uncertainty. So I want to mention it because maybe in the future it will develop a lot, it will be important. But at the moment, the ages we are getting with this are a bit, well, have a large uncertainty. The method is that there are two ways, actually. One developed by Ness et al., they are very similar, and another by Martig et al. Ness et al., Melissa Ness is the one that is an astronomer that developed a code called the Canon that makes full spectral fitting, so fits the whole spectrum in a region, no matter how big, and determines simultaneously all the parameters, in principle as many abundance as you want, because it has been trained, if it has been trained on a set of many spectra with different parameters known from the start. So it is kind of a neural network code. Specifically, it is called a data-driven code because it really interprets the variations of different parts of the spectrum according to what it learned from known data. Okay? So without putting too many physics in it, it just said, I have here a sample of spectra with known temperature. I see that this part of the spectrum is varying with the temperature, this other is varying. So I can model analytically how does it vary and then derive the temperature without caring if this is an iron line with excitation, etc. Just modeling the data. So with this approach, the code, the Canon, in practice finds that there are some feature of the spectrum that depends on different parameters. I know it is hard to read. I try to put it as big as possible, but here you can see a region of the spectrum, and how this same region is sensitive to different parameters. For instance, the one that is very easy to read is the purple line. Here it says iron. So this part of the spectrum does not depend on iron. This is a coefficient of the dependence on different elements. Then this is very sensitive to iron. Of course, it is an iron line. But then you lose sensitivity, then you are sensitive again, you lose sensitivity, etc. No? So this is how sensitive it is, this region of the spectrum, on this parameter. And here it says log mass. It is a pink line that I can follow like that, okay? More or less. So what this thing is saying is that there are this feature of the spectrum. If you notice when you are at home and you see it bigger, all the CN lines, in correspondence to all the CN lines, you have sensitivity to log mass. This means that in principle, if you could distinguish the dependence on log mass from the dependence of all the other parameters, which is a bit tricky, but in principle, if you could do that, you could measure mass from the spectrum. If you measure mass from the spectrum of any giant, then you will know the age of the stars, okay? Because, I don't have a slide on that, but I hope we can agree on that. Stellar populations of different ages have different absolute magnitude of the turnoff, so they have a different mass for the star that is evolving off the turnoff. Please raise your hand if this is not clear. It's something I give from granted, but I could draw something to clarify it if you want. I should. Denise is raising his hand. So let us. In mass, meaning that up here you have the star with, I don't know, 0.5 solar masses, you have 1 solar mass, here you have 1 point solar mass, 2, 5, oh no, sorry. 'Be the same as the mass at the turn. Forgot. Sorry. Too many things in my hand. So this will be also 1.00, 1.00, 1.01, 1.02, and so on, okay? So if you know the mass, if you measure a star that is there, for instance, and you can measure its mass, you know that it's 1.01, then you know that this corresponds to a stellar population that is already evolved, and so it is, in this case, this is a population of 10 gigayear. Okay? This is a population of 1 gigayear. And this will be a population, I don't know, 5 gigayear, perhaps? Okay? So there is a correspondence between the mass of the star that is evolving in the red giant branch and the age of the stellar population, of the parent stellar population of that star. Is it clear? Questions? No. Let's. The relation is between the age and the star at the turn, the mass of the star at the turn off. But because the mass is the same all along the red giant branch, there is a relation between the mass all along that and the age. Okay? So if with this method from the spectrum you can measure the mass, then you can measure the age. This plot is because after she measured that with the code that is kind of a black box in the sense that there is no physics in the code, it's just interpreting data based on some known data, she verified that the ages that the Canon, the name of this code, measured is the same as the age of Kepler. The age of Kepler is a satellite that does astroseismology, so measured the mass of a star based on the seismic oscillation of the surface of the star, actually the whole star. So these are ages very accurate, we believe, very well measured, and if they agree with the masses, if they agree with the masses and therefore the ages measured from the Canon, we think we are doing it properly. Why do I say that it's very uncertain at the beginning? Because this measurement is very uncertain. Is it true that apparently the CN feature in the spectrum have a dependence on mass, but they also have a dependence on many, many other parameters? And so you have to be able to disentangle the dependence on all of them. Marie-Martigues et al. At the same moment also realized that there are some features in the spectrum that depends on mass. In particular, she found that it's similar, it's the same concept behind that. So the ratio of the abundance of carbon over nitrogen has a correlation with mass. She's been analyzing a sample of spectrum from the survey sub-survey that is called APOCASC. These are stars observed in apogee, so we have high resolution near-infrared spectra for these stars, and they are also part of the Kepler observation. So we have masses from Kepler and high-resolution spectra from apogee. This comes from high-resolution spectra, this comes from seismology. For these stars in common, she could draw two relations between the mass and what she measured in the spectrum. The relations are two because in principle, what we know of stellar evolution tells us that the relation should be different. Should be different for stars in the lower red giant branch and for stars in the upper red giant branch. Why? I mean, lower and upper is separated from the red clump, more or less. Why? Because, as some of you pointed out yesterday, there is some extra mixing in the envelope of a star that could change the surface abundance of this element while the star is evolving in the red giant branch. So the star in the upper red giant branch experienced, most of them, this extra mixing, while the star in the lower red giant branch did not. So in principle, this relation, if what we understand of stellar evolution is correct, should be different. But it is not different, and so this is something we don't understand, we just observe. So if we believe in this relation, then we can measure Cn from the spectrum, the ratio of carbon over nitrogen, and then derive the mass. This is something I draw just to remind you that a population that has a star of 1.6 solar mass evolving in the red giant branch is a population of 3 giga-year-old. Instead, a population that has a star of 1 solar mass evolving off the red giant branch is a population that is 10 giga-year-old. So with this method, she could assign an age to a population. Notice that this thing is very flat for a huge range of age. So it is an uncertain relation, but it is something that we could do, and 3 years ago we couldn't do it. So at the moment it's the best we have. It's not perfect, but we could, with some caution, we could use it and learn something from that. So Melissa Ness, the one of the first method using the Canon, could make a map of the ages of stars in our galaxy. The color code gives the age between 0 and 12 giga-years. This is the sun. This is more or less the galactic center. So what she found, this was a press release of 2 years ago, is that stars in the inner solar circle, so inside, stars between the sun and the galactic center, are predominantly old, while stars outside the solar circle are predominantly young. This is something that we knew. We think that our galaxy was built inside out. So the oldest stars are in the center and the youngest stars are in the outer part. So it wasn't a new result, but the technique was very new. And the fact that in principle you could measure ages for many, many individual stars, so you could map the whole galaxy. You could make an age map of the whole galaxy. Okay, this is some caution about this. You can read it at home. It's just the fact that if you don't put extra mixing correctly, then you have a wrong calibration between age and cyan. I want to go now to a different topic. Let's assume that we can derive a metallicity distribution for a stellar population with all the caveat, with all the precautions that I explained. You have to sample the color. Hopefully you need high resolution spectra, etc. Finally, we have iron, for instance. So we could construct the iron distributions, number of stars versus iron abundance for a sample of stars. What do we do with it? Now that we obtained it, how do we interpret? What do we learn about this population? In order to explain what can we learn, let me start from a very simple model, very unrealistic model, but very simple, just to have a few fixed ideas. The very simple model is the closed box model. It is a model that assumes, here are spelled the assumptions, but most accurately, but just qualitatively, we are taking a box of gas of the universe with primordial composition, so 3/4 of hydrogen, 1/4 of helium, and just a bare trace of metals, and then we let it evolve. We convert the gas into stars, and then these stars will explode at some point, so they will return enriched gas to the medium. We let this enriched gas form new stars, and so on. We let the box evolve until it stops, until it has finished all the gas, and it cannot, and no new supernova will explode and will be able to form stars because the massive stars already exploded at the beginning. Then the low mass stars have a much lower rate to explode only if they are binaries and blah, blah, blah. Anyway, at some point, this box will be all converted into stars, and you can go and measure the metallicity of all the stars. To model this box is extremely easy, and in the end, you have an analytic expression that tells you that the distribution is like that. Okay? It's almost a Gaussian, but it has a longer tail on the metal poor side. This is just the same thing if you want to put it, to plot it in the linear scale. Remember that this is almost exactly the logarithm of this other thing. So I put it because it might be strange for you to see this distribution because you think, okay, I start converting all the gas into stars. At the beginning, I should have a lot of metal-poor stars, and then the metal-rich stars are only the ones that formed later with the material enriched from the supernova, so they should be less. But from here, you don't have this impression. In fact, linearly, it is like that. You have many metal-poor stars, and then fewer and fewer metal-rich stars, but if you plot it logarithmically, you have a bump here, okay? Let's don't talk now about the yield. Let me go here before. In practice, in your very simple toy model, if you change the initial mass function, so if you change the distribution of the mass with which the stars are born at the beginning. When you convert the gas into stars, you have to assume how do the stars distribute in mass when they are born from a box of gas. If you change that, in practice, you are changing the peak of this distribution. So you could model what you observe constraining the IMF from the position of this peak. You could model this with other stuff. We know that the closed box model is very unrealistic because we don't have anywhere, much less in a galaxy like our own, a box that is evolving in isolation. For sure, we will have some exchange of gas of this box with the rest of the galaxy. For instance, gas may fall in or may get out. At the very minimum is minimum interaction. So if you put some infall, if you let some fresh gas falling into your box, then you move the position of this side of the distribution. You don't touch the peak too much, you don't touch this, you don't need to read that. It's just different prescriptions from the infall. If you change the prescription of the infall, you change a little bit this side of the distribution. And if you let gas going out of your box, you change, where is it? I don't have it. You change this side of the distribution. So if you have a mismatch between the data and the observation in here, you may change your prescription of the outflow and get the model fit the data. So what do I want you to take home from that? Is the following. In principle, you could get a very simple model with some gas being converted into star, eventually receiving new gas, eventually letting some gas out. You could twiddle this model in order to fit your observations. You could change the IMF to fit the peak. You could change the inflow to fit this side. You could change the outflow to fit this other side. In principle, you can more or less fit a distribution. However, there are 2 points. One is you have many a periglia. How do you say la periglia? You have many free parameters. Yeah, I wanted to say specifically the thing you move. Anyway, you have many free parameters to fit some data, so you could play with that and fit almost anything. So there are degeneracies, to say it properly. However, if you have a distribution with 2 peaks, like this, very far away, there is no way to fiddle with your model in order to take a bimodal distribution. So what do we do in practice when we have a distribution in iron? We use it to constrain loosely the infall and the outflow, but we use it a lot to constrain how many populations you have, how many stellar populations you have there, because if you have a single peak, most likely you had a population that formed together. Maybe you don't manage to constrain exactly the gas exchange and the parameter of the inflow, etc., but at least you know that it's one population. You could play with those to have some idea. But if you have a bimodal or trimodal distribution, then this is a strong indication that you have different populations, so group of stars coming from different environment getting there, okay? And we will use that in the following. Now this is another plot that deserves at least 10 minutes, because this is probably the plot that we spectroscopists, observational spectroscopy, use the most. And it is a plot that it is a bit complicated, a bit tricky to understand for young students, at least it was for me. It is a plot showing, so let us take the time it takes to understand this plot right. It is a plot that has metallicity here, so abundance of iron, and here it has alpha over iron. Alpha stands for any of the so-called alpha elements. These are the elements whose nuclei is a multiple of an alpha particle, so 2 neutrons and 2 protons. In practice, these are oxygen, carbon, titanium, silicium, sodium, calcium. Magnesium, thank you, is the most important perhaps. Okay, so you can put any of these elements. The plot will be very similar for any of these elements. I'll show you in a moment why. I'll tell you in a moment why. Keep in mind that this axis is roughly an axis of time because, as we discussed yesterday, the iron content of a stellar population increases if you keep forming stars. So the stars that are on this side of the plot are the stars that formed later from an enriched material, while the stars that are on this other side of the plot are the stars that formed first from a more pristine material. So this is kind of an axis, a time axis. This plot usually shows an E at some point. So stars distribute here in a flat, they have a flat distribution here, and then at some point they start falling down. Falling down means that the abundance of the one alpha element over iron starts to decrease. In practice, if you increase the star formation rate of a population, you move this knee in this direction. If you increase the IMF, if you fiddle with the IMF, you move this plateau up and down. Why? Because we can divide this plot into regions. This region is dominated by the enrichment by supernova 2, more specifically by core collapse supernova. The massive stars that at the end of their life explode and enrich the material. This other side of the plot is a plot where the enrichment is dominated by supernova 1A. These are the binary stars in which you have a red giant and a white dwarf. The red giant throws material on top of the white dwarf until it becomes unstable because it reaches the Chandrasekhar mass and it explodes. These stars explode later in the life of a stellar population because these are low mass stars that evolved all their life, the main sequence, the RGB, they became a white dwarf, and only after they were a white dwarf, they may eventually explode if they have a companion that is on the RGB. So this supernova exploded at a later time. In fact, they are on this side of the plot, and this supernova exploded at the very beginning of the formation of a stellar population. This moment, this point, the knee, can be identified more or less with the specific moment in time, about 0.5 gigayear. This is the moment in which supernova 1A start to explode in a stellar population. So what this plot is telling us is that when the enrichment of the medium is dominated only by supernova 2, you have a fixed constant ratio of alpha element over iron, because supernova 2 contribute many alpha elements and some iron in a more or less constant ratio. However, when supernova 1A start to explode, supernova 1A are the highest contribution of iron in the universe. They produce a lot of iron, they almost don't produce at all alpha elements. So when these supernovas start exploding, you have a lot of iron and very little alpha element. So this ratio starts decreasing. Okay? So the reason why this is flat is because this supernova contributes a lot of both of these elements in a ratio that is fixed if it is fixed the IMF. If you change the IMF, you change the ratio of supernova coming from an 8 solar mass stars compared to the supernova coming from a 50 solar mass star. So you change this ratio a little bit, but you don't change the fact that it's fixed, if the IMF is fixed. When you arrive at this point and supernova 1A start exploding, then the enrichment is different because you enrich more and more iron and don't touch the alpha element, and so this thing goes down and down. So, in practice, when you measure this plot for a stellar population, now we will see some example, the trick is to identify this knee, and we know that this knee corresponds more or less to 0.5 giga-year. So if a stellar population had a very fast star formation rate, it means that the stellar population formed many, many stars before 0.5 giga-year, because it was fast, right? If you have a fast star formation rate, suppose you might form many stars before that point. I don't think I need a light. I will just draw. This will be solar mass per year that you form in a stellar population. A fast star formation rate will be something like this, right? Meaning that you form a lot of stars before 0.5 giga-year, and then you form nothing anymore. And a slow star formation rate, is something like this. Yes? So you form stars all the time for an extended time, but a little of them. Okay? So if you have this star formation rate, you have all your stars formed before the 0.5 and nothing afterwards. So if you construct this plot, you will have all the stars in here, many points in here, and right there, nothing, or a little bit of them. So for this population, that plot, iron and alpha over iron, will be like that. Many of these, until you reach a lot of iron, because anyway, if time goes by and you form a lot of stars, you have many supernova 2 exploding, so you are still enriching of iron, but you are enriching of alpha at the same time. So these things stay flat. And then you form just a few stars in this region, so 3 there. Instead, in this case, that plot will be like that. Will be a few stars before the knee, and then all these stars will be formed after supernova 1A are exploding, so all of them will be enriched in iron and not in alpha element. So it will be like that. So by estimating the position of this knee, we can distinguish between a fast star formation and a slow star formation, okay, for the population. I'll show you some example, and then I will stop to check if you are okay or we got lost. This is an example. These are stars. The green, cyan, and red dots are stars in our own galaxy. We live in a massive galaxy that, compared to other small galaxies that we have nearby, had a relatively fast star formation. So we have a plot that is more or less flat, not really too flat, but then at some point we have a knee that is at, I don't know, minus 0.8 perhaps, and then it starts going down. Instead, if we go in dwarf spheroidals of the local group, much smaller galaxies that had a slower star formation rate, we have these points. So we have, in this plot, we have the knee at -2, so much more metal poor, and then all the stars there. It means that those galaxies formed stars very slow. So they formed 3 stars, maybe, before 0.5 gigayear, and all the other stars at later time. Many of the stars when many supernova 1A had already exploded. So very slow the star formation rate. Instead, our galaxy formed all these stars before 0.1 gigayear. That is a very short time, right? So after 0.5 gigayear, from the first star that formed in our galaxy, we had already all the stars in place. Well, and kept forming stars later on, but at a much slower pace. Okay? Is this clear? Yes.
0.5 gigayears as this.
0.5 gigayear is the point in which you don't form a... After 0.5 gigayear, all the massive stars with mass above about 8 solar masses have already exploded. So you don't have any core collapse supernova anymore. And you start having these other ones that can explode until later time. Okay, so this is more or less the lifetime of 8 solar mass stars.
So of course, if you go to different metallicities, if you go to dwarf, those who are talking about, this will change a bit.
Change a bit, but the lifetime of an 8 solar mass stars changes really a little bit. Okay. Now, if you go to any isochron, to any stellar evolutionary model, you will see that the lifetime of an 8 solar mass stars is a bit shorter than this. So don't quote me wrong. It's a bit shorter, but then you have to enrich the medium, the supernova have to expand, the new stars, it's not really instantaneous, the recycling. So in practice, this is, if you model this thing properly, this is more or less correspond to 0.5 gigayear, even if it's a little bit longer than the lifetime of an 8 solar mass stars. More questions on this topic? We will use a lot this diagram, so it is better that we understand it now. Okay. And so let's stop talking methods and start talking about results. A few years ago, Thomas Bansby et al. Measured many alpha elements and iron from a sample of very high resolution spectra, exquisite quality spectra of stars near the sun. He could construct this plot in which this is titanium abundance over iron, and titanium is an alpha element. So titanium is an element produced a lot by core collapse supernova. And this is iron. He found that the stars he could measure distribute in two sequences. A sequence of high alphas that then has a drop there, and another sequence for which he could actually guess more or less the knee, and then it goes there. Forget about the size of the symbol for a moment. It's clear that here this thing is bimodal, right? There is a high alpha group of stars and low alpha, low titanium in this case, group of stars. So he could verify, we'll see in a moment how, that these stars had a higher position in our galaxy, a higher altitude over the plane, and these stars have a lower height over the plane. So he associated these stars to the thick disk, and these other stars to the thin disk of our galaxy. From the spectra, he could also measure ages. Now we know how he did it, right? So in this plot, he shows the symbols according to the age. And he found that stars on the upper sequence are older than stars in the lower sequence. You see, these are a smaller point. So the age of the stars in the thin disk, it's lower, closer to 1 gigayear, while the age of the stars on the thick disk is between 10 and 15. So from the interpretation of the plot that we were discussing a moment ago, we know that the thick disk has a fast star formation because the knee of the thick disk is relatively metal rich, is minus 0.3 more or less, no? Instead, the thin disk have a very extended and slow star formation like this one, because you could guess an E here, minus 1.1 more or less, and then most of the stars in the thin disk formed after 0.5 gigayear. So after supernova 1A started to explode. So here we learned that the two components had a very different star formation rate. And also, as it seemed, a different mean age. Don't remember why I have this, just for you to see it better maybe. One of my first slides was this plot, the Tomre diagram, in which you could see that stars that move in the same way as the sun, in particular that have the same velocity of the local standard of rest, so 0 here, could be associated to the thin disk because they have a little transverse velocity. They just rotate very well behaved, close to the circular velocity in the disk. And stars that have lower rotation velocity and higher transverse velocity could be associated to the other components. So to components that move more, have more disordered motions, and so they don't stay really in the disk. They get farther and farther away from the disk. This was just for you to remember the diagram because Thomas Bensby constructed the same diagram for the two samples. Actually, he separated the stars in ages, so in size of the dot, or to say it some way, and said that the small dots, the stars that predominantly belong to this sequence, are more concentrated around a motion similar to the motion of the sun. And just few of them had a more disordered motion. Instead, the older stars not only defined a higher sequence in alpha, but also have higher transverse velocity and smaller rotation velocity. Of course, and this is important, there is a large overlap between the two. You don't see the stars only up here and the stars only down there. There is a large overlap, and this is very important to realize, because one of the biggest problems in studying galactic component is to separate them, to decide, okay, now I want to study the property of the thick disk. I look at the sky and there is a lot of small points. So what is the thick disk? How do I define the thick disk? I could define the thick disk as those stars that are high above the plane. Okay, I could decide that, but I could have in that sample many stars that belong in fact to the halo or the thin disk anyway, and I see them high in the plane because the halo is everywhere, and because the nearby star of the thin disk anyway will look high in the plane, right? I could decide to separate them by alpha element. I could make a cut in here and decide, okay, this is the thick disk and this is the thin disk, okay, could be, but then I will not be able to study the star formation rate anymore because I am defining them according to the star formation rate, see? Or I can separate them kinematically, and then I could study their distribution in alpha, in ages, but I could not constrain their kinematics because I bias the kinematics in order to define the sample, you see? So it is important that we use different approaches to then cross-match them and try to have an idea. In this case, he's seeing that we have two components. I labeled them. I could have not. I mean, what we know for sure is that in the solar neighbor, there are a group of stars that formed fast and are on average older, and another group of stars that formed slowly and are on average younger. And then from this plot, we see that on average, the young stars, those that formed slowly from an enriched material, tend to move like the sun. Instead, the older star, the one that formed faster because they have a high alpha over iron ratio, tend to go to move different from the sun. This is what the plot is saying, okay? So we can start defining two components with these properties. Another way to separate the two components, is to separate it only spatially, what I mentioned before. You can take our galaxy and select sample of stars that stay high in the plane, or a bit lower, or just in the plane. This is what Marie Martig did a few 3 years ago. The lines here correspond to these colors, and she is studying as a function of galactocentric radius, so as a function of this. I don't know why she didn't plot it the other way around. Sometimes I get mad at papers because it will be so intuitive to have 4 kiloparsec on this side and 15 on this other side, and it doesn't. Anyway, so this is the other way around, okay? This is close to the center, and this is far from the center, and the color correspond to this. So this is, you cannot see it, so I wrote it there, is the mean age of this population. I didn't mention it, I'm sorry, she had spectra. So this is age, and alpha over iron, in this case over all the metals measured from the spectra. We know how. So the stars that are closer to the plane, actually in the plane, and here is the range, when you are at home maybe you can read it, the range of height, are older only in here. Only at 4 kiloparsec they are old, around 9 gigayear, but very quickly they become young when you move outward. Very quickly they become 4 or 3.5 gigayear old, all the way down to there. When you move at higher rate from the plane, you get on average older and older ages, and also milder gradients. Okay? So what this is telling us is similar to what we saw in the other plot. Stars that stay above the plane are on average older. Stars that stay in the plane are on average younger. But when you go sufficiently far away in the galaxy, everything is younger. So this tells us that our galaxy formed most likely inside out, or at least we have the older star close to the center nowadays, and the younger star farther there. In this plot, we are plotting median alpha over iron, or in this case over all the metals, for the way she measured it. So this is star formation rate. This is telling us how fast the stars in each position formed. And we see that in the plane, stars that are close to the center, so at 4 or 5 kiloparsec here, had a fast star formation rate, but very soon they have a very slow star formation rate, okay, because they have low alpha. Instead, when you move up in the plane, all the stars that you find there formed very quickly because they have high alpha. And actually in this plane there is kind of a bimodality. You see 2 curves close to each other up there and 2 curves close to each other down there, similar to the other plot we were seeing. We have a thick disk, let me call it by its name, a thick disk up here that has high alpha, unless you go very far away out from the solar circle, and a thin disk closer to the plane that has low alpha everywhere, so formed slowly. This is my last slide. I don't know what time is it. It's okay if I stop there? Fine. So what did we see so far about the thin disk, the thick disk? I promised I would talk about all stellar populations. So I mentioned the thin disk only barely in comparison with the thick disk. We will not see the thin disk in these classes. So let us concentrate on the thick disk. Stars in the thick disk have mean iron of minus 1.5. I didn't mention it explicitly, but we have the iron distribution here. It's a question of see where are the stars in iron. More or less, they concentrate on this point with some distribution. So they have a mean iron of minus 0.5. They have ages around 10 gigayear. They have a rapid star formation because their alpha over iron is on average very high. They dominate at height larger than 1 kiloparsec, as we saw from here. No? This is 1 kiloparsec. So the red stuff with high alpha dominates above 1 kiloparsec, they become negligible outside the solar circle, because at 8 kiloparsec, more or less, you don't have anymore a population with high alpha, you don't have anymore a significantly old population. So a plot of our a sketch of our galaxy will be something like this. We have a thin disk that flares up. We will see this maybe tomorrow. And the bulge in the center, and the thick disk that it's thicker, as the word says, thicker, older, had a fast star formation, but it doesn't extend outside the solar circle. This will be the sun, more or less. This is new. We learned this only relatively recently when we started having precise position distances from Gaia. If you see a plot, an older plot, actually the one I showed yesterday in my second slide was an older plot. He had a thick disk extending all the way to the periphery of our galaxy. Now we think that the thick disk is concentrated inside the solar circle. Okay, so I can stop here, I think.
So thank you, Manu, for this very nice lecture. So
thank you.
First question there.
You speak about the alpha-iron ratio change with the IMF. When you use the stellar population models to fit in galaxies spectra, we're using different stellar population models with different IMFs. How you suggest to choose the best IMF to your model during the fit, considering that you have a salpeter, Krupa, and so on?
The ideal would be to use the IMF that has been measured for that population. So, for instance, people, because it's me, measure the IMF of the bulge. So use that, and you are sure that is the IMF. Other people measure the IMF for the disk. If you can use that one when modeling your disk, you are fine. To be honest, you are kind of lucky, because we don't see many variations of the IMF in different environments. So if you stay to some population close in terms of metallicity, for instance, you are more or less fine. There are reviews. One that I know of by Nate Bastian a few years ago that plot the slope of the IMF measured in many different environments, and so you could use that, for instance.
Do you know why in these abundance ratio plots the sequences always seems to converge towards the solar ratio and not continue? I remember that at least 10 years ago I saw some papers saying that the steep decline should continue to subsolar ratios, but
yeah,
most of these abundances now don't
they
look
flatten.
like that.
I read in a few papers when I was preparing this class that this flattening is not very well known. We don't have an interpretation for the flattening. However, I would put a few words of caution there, because these are very metal-rich stars. You have seen the spectrum. So this is the most uncertain region to be measured. So I wouldn't promise 100% that this thing is really flat here. It's just the most uncertain place of the plot. But we don't know why it flattens.
When we plot the age of open clusters and the distance of these open clusters to the galactic plane, we can show that the young open clusters are near to the galactic plane and the old are more far the galactic plane. The difference of star formation rate can you explain this process?
Yes, there is the difference in age should explain this process, right? So basically you are saying that you see this. This has been traced with field stars, but you would find a similar plot with open clusters. So when you stay high from the plane, you find predominantly old cluster, and when you stay close to the plane, you find predominantly young clusters. So it is this plot. Means that the clusters, at least the open clusters, form together with field stars. Good.
Okay.
Any other question? Didn't you see the question? Well, I can have one.
Yeah.
Here we have lots of different students. So some of them are working on photometry and the others with a spectroscopy, you know, mailing. So could you comment a little bit, because you show lots of CMD diagrams and luminosity, temperature. Can you comment a little bit about this? When you come from the photometry to spectroscopy, from the observations to the theory, what do you have to take into account, you know?
It's a huge question, yours. So let me, let me make a philosophical point. Just, I think that we shouldn't be. When you are very young, you start specializing in a technique, which is good. It's better if you master the technique you're using as best as you can. But in the end, we are scientists. We want to solve a problem. So the approach I decided to use in my life, it takes some time, but is to choose the problem and then use all the technique that could attack the problem. It's like you have a crime to solve. You want to find the killer. It will be absurd to say, okay, I only use DNA analysis, and I can investigate the crime only via DNA analysis. Okay, it's limited, right? It's best if you make the DNA analysis, if you take the fingerprint, if you talk to the witness, if you use all the technique to try and corner the killer. So that will be, then you have more work. Then you write a proposal. Yeah, so I hope that with time, my advice will be to start mastering different techniques. So when you, because also, as she said, when you get new data, typically you find some conflicting results. So when you find a new problem, and if you say, I cannot investigate this problem because you will need that technique to understand it, it will be a shame, right? So new problem come out when you keep investigating. And it's good if you try to master different techniques to attack them.
I have a question, and this is a question much more from yesterday than from today. But remember you're saying, like, based on the distribution of, well, mass and whatever, the different components of the galaxy, that the halo, it would be the one you would leave for later. Well, and then after you said that if you use the turn-off way of determining age, for the halo would have, you know, for whatever that it's between 80 and 13 giga years old, it's really hard to do. And then I think, how can you solve this? Because, you know.
Well, tomorrow I'll show you a beautiful fit of the color magnitude diagram of the halo obtained with Gaia. Because Gaia gave us a lot of new information, especially for the halo. I think that for the moment, the main revolution concerns the halo.
Okay.
I want to apologize to the people who study in the halo. If I tend to always say this is 1% of the galaxy, let us forget it. It is a 1% that is critical in a sense, because we think it is the first 1%, so it will be important to understand how did it form. But I think we shouldn't make the mistake to take it as a prototype of the galaxy. For instance, the halo is full of stream. We know that there is a large, maybe the whole thing, fraction of the halo has been accreted. But we shouldn't jump to the conclusion that this means that the whole our galaxy was accreted. Maybe some cosmological models say that, but if you form the halo by accretion, means that you form 1% of our galaxy by accretion. You didn't solve the problem of how did our galaxy came to be like this. You just solved that, okay, this part came from accretion. And then we have the other 99% to understand, okay?
Extreme metallicity will be in the halo. So
Yeah.
with all of these things, we are not ignoring, but how can you get to the very low metallicity in the galaxy? You do not
No,
analyze
you study
deeply
the halo. I
the-
didn't meant to be. You need to forget about the halo. Let
No, no,
us
I know,
study
I know,
the
I know
halo.
this, but I'm really interested in the halo. But I think that this to go to the very low metallicity things,
Yeah.
we need the halo. There is no other way. Yeah.
Absolutely, yes. Yes.
Another student question?
Sorry, if I got it right, so the thick disk was formed quickly, and I mean, within
Long
7 and
time
10
ago, yeah.
gigayears ago. But so what is the current scenario about the formation of a disk? Maybe you'll talk about this in the next slide.
Tomorrow, we think that there
okay.
was a major accretion in our
it's-
galaxy that thickened the disk. And Gaia gave us some support, strong support in this direction. So we think that if there wasn't this accretion, maybe we will now have only a thin disk, very dense. But at some point we got this huge kick. And so the disk that was in place so far heated up. And then a new thin disk started to form.
So, but it was a major event, not a...
Yeah.
Because I was thinking that thick disks were a result of minor majors. So
This is what we thought until last year.
Okay.
But then there was some Nature paper arguing that what we see in the halo is the demonstration that we had a major accretion. I tell you tomorrow. Tomorrow
Okay.
I will talk about this a lot.
spoil.
Any other question? No? So let's thank Manuela again, and then you can go to the coffee break.